So here we are on the plot file, we are going to plot electrical momentum, we are going to plot angular momentum, we can plot both electrical momentum and angular momentum, we can plot also angular displacement because we have fitted a sensor now, and we can also see the phase plots. So let us have a look at our system and let us simulate it. See, I have taken some values and we are just performing a simulation and done. Now the values which I had chosen were a little stiff, that is why it took a little time to integrate. It depends upon, because this Runge-Kutta which is there in MATLAB is an adaptive Runge-Kutta, adaptive solver. So it checks for the error. If the error of integration is beyond permissible limits, then it reduces the sampling time. When it reduces the sampling time, your sampling interval gets reduced, and so every time it checks for the error, and if it is still not within the limit, it further reduces the interval. So this process goes on till it gets a reasonable amount of error which is within limits, and then it performs this operation throughout. So it's an adaptive Runge-Kutta, and that is why it could take more or less time depending upon the stiffness of your system, or it depends upon the occurrence of transients in your system or discontinuities in your system, okay, or a few more factors. So here you have the electrical momentum shown here, and this electrical momentum is a measure of the current, okay. So L into I, L being constant, so you will get a quantity which is proportional to the current. So it's telling you that if you apply this, after some time it's going to be like this. Angular momentum of the rotor is like this, and electrical momentum and angular momentum both plotted. You can see electrical momentum is almost flat here on this, but it's because the scales are totally different. So it's not always that you are able to make a proper comparison. This is the angular displacement, and as it is understandable, it just increases like this. This is a plot, phase plot. I have taken some, let's take some variation of parameters here. Let's vary the parameters. Let's say we take, what shall we change? Let's change the armature resistance itself. Let us take armature resistance as 1. Okay. So we will take armature resistance as 1 instead of 10, and let us see what happens. So before that we have to save our file, and then we execute this. Now you find that there is some slight change in the response. Earlier you had, the response was much quick, okay, and now you find that it is a little sluggish. It is taking a little. What you did was you reduced the armature resistance. So this is quite understandable because you are actually playing around with the time constant of this system in case of linear systems. So the angular momentum of the rotor, which is a measure of the angular speed, this is also going to catch up a bit sluggishly. So you can see how the angular displacement is changing. So you can study the system in this way. You can also see the effect of maybe the modulus. Let us say you take, shall we weaken this a little? Mu, we will just reduce it a little and see what happens. It's a little bit of mischief, but let's reduce it by this order and let's see what happens. So we run this simulation again. Yeah. So we are getting almost the same thing, but of course it has become pattern looks more or less the same. So you can try out different parameters and you can study the response. Okay. The next, let us take another example, and this example is, I'll close this part. Let us see another example, and that example is let us take this is a mechanical system. In this mechanical system, it is a rail problem. So I'll take this example of the rail. And do we have a plot? I think I have not taken this. Perhaps we have a diagram somewhere. Yes, we have this. I think we also have it in the, no, it's not numbered. So we can use this one itself. Yeah, it's okay. So we will use this diagram, and we will start with our example in MATLAB. So we have the problem on rail. This is also one of the examples which I am going to provide you. And in this, we will start with our main file. I will remove the other files, I will close them from the editor. We have exactly the same structure. In this, we specify the time span as 0 to 100 seconds. We have x naught, we are specifying here the states as follows. The initial conditions are, the first state we will take as the momentum of the engine. So first I think I need to change this. Yeah. So we are going to change. So where we have the momentum of the engine as our first state, and this is 0. So our engine is at 0 velocity, it's at rest. PA is the translational momentum of bogie A. This is also 0 at time 0. Then we have the momentum of bogie B. This is also 0. We have the coupling over here, the state associated with the coupling, QAE. And this also is 0. We are taking as if it is not deformed. That means it is not deformed. And QAB is the state associated with this. It has not appeared in the figure, but you can treat that as one more state here, which has not been shown incidentally. So this is QAB. And that is also 0. So everything is 0 to start with. Okay. And then we take the parameters. We take the parameters as mass of the engine is taken as 20,000, mass of the bogie A as 12,000 kilos, mass of B is 12,000, RAE, that means the damping for this coupling has been taken as 5,000. This will be Newton second per meter, and this will be RAB, this is also 5,000. RF, that is the frictional braking, right now we have taken it as 0. KAB as 150,000, and this is in newtons per meter. Okay, you could take it more or less. SI system of units has been followed. The next is Yeah. So the next is we specify this differential equation file which we are obtaining from bond graph. It's over here, rail ODE. We'll open this selection, and this is exactly the same way as we did, and I'll explain to you the coding. I think by now you are going to be pretty familiar with it, but just as a sort of exercise, I think it's good for me to go through it once. So we have the first input, this as Tx, and output is out1. The first state is, okay, all this has been already explained. We have specified the initial conditions also, and we ask our first set of questions. What do the elements give to the system? So in this you can see we start with the sources. Effort 4. What does this give here? Effort 4. Effort 4 I have taken over here as a flat, a jerk, suddenly a pull that is applied, 5,000 newtons. It could be more, it could be less. The next is, what does this element give to the system? It gives flow 1. Flow 1 is P1 upon ME, okay, in terms of states and parameters. Then you have flow 2. What does this element give to the system? It gives flow 2, and that is PA upon MA. What does this give to the system? It gives PB upon MB. Flow 3. What does this element, this C element, give to the system? Effort 8. If it is a linear spring, you can just write it as KAE into QAE, and here you can take this as KAB into QAB, and this becomes effort 13. So you have got all your questions for the spring answered. Then you ask for these dampers. What does this R element give to the system? Effort 9. Effort 9 is actually equal to RAE into flow 9. What is flow 9? Flow 9 is equal to flow 7. And flow 9 is equal to flow 7, and flow 7 is flow 6 minus flow 10. So you can write flow 9 as flow 6 minus flow 10. What is flow 6? Flow 6 is the same as flow 1. Flow 6 is the same as flow 1. And what is flow 10? Flow 10 is the same as flow 2. And both flow 1 and flow 2 have been defined earlier on line 20 and 21. So this part is done. Then come to this. What does this R element give to the system? It gives effort 14. Effort 14 is equal to what? RAB into flow 14. Flow 14 is equal to flow 12. What is flow 12? Flow 11 minus flow 15. So flow 14 is flow 11 minus flow 15. Flow 11 is defined on line 31 as flow 2, because flow 11 is the same as flow 2, and flow 15 is the same as flow 3. Both flow 2 and flow 3 have been defined earlier, okay, and they have been defined here on line 21 and 22. So done. Finally, if we are going to have a braking force on the engine which is viscous, we could have it non-linear also, or we could apply it at any other time. Just to represent it, we write it as effort 5. Effort 5 is RF into flow 5. And here flow 5 is equal to flow 1. And flow 1 has already been defined on line 20. Done.